In this video, we're going to be discussing the Epsilon-Delta limit definition, which is the rigorous definition for the limits that you'll see in a calculus class. And oftentimes, it's taught that a limit exists at a point if the function approaches this value from the left and it approaches from the right, the limit exists. There's some other tricks that you learn to compute limits, but to learn this, you can really just forget about all of that. This is building the definition of a limit from the ground up, and you kind of get an idea of what a limit actually is. There's no ambiguity here. Let f be a function from the set S onto the real numbers, and let C be an accumulation point for S. And C being an accumulation point for S just tells us that we have this point C, and we can move whatever distance we want from this C, and we're contained in the set. So if our accumulation point is 3 for the set S, then we can be at 3.0001, and we are still contained in the set S. But C doesn't have to be a point of S itself. That's an important thing to know. But we say that the limit of f at this accumulation point C is equal to some real number L if, for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in the set S, where this inequality is true, where we have the distance from the accumulation point, x's distance from the accumulation point is less than this delta, then we have that all x that satisfy this inequality plugged into the function value, their distance from the limit value L is less than any given epsilon greater than 0. So what exactly does this mean? Right here we have a graphical representation of what's kind of going on here. We have a distance epsilon from L. We have, say, L plus epsilon, L minus epsilon. Since we're considering the absolute value, it can move in either direction, and we still have that distance from epsilon. We're saying that given some epsilon, give me any distance from the limit value on the curve. Then we can find some delta greater than 0 where we can constrain the distance from the accumulation point C, and as long as it's less than that delta, all the x values that satisfy this inequality will be less than this epsilon when plugged into the function value and subtracted from the limit. So give me some distance from epsilon, or distance from L, the limit L. We can always find some delta that keeps the domain's values constrained in such a way that the distance of the function value at these x values and the limit, the distance between the two, is less than any given positive epsilon. Now, that's kind of a mouthful, and it might be a bit confusing, but it may make a little more sense if we introduce some concrete numbers. If we're saying for any epsilon greater than 0, we can choose the smallest epsilon we want. Let's say we have epsilon as 0.0001. Then there has to be some delta, assuming that the limit exists, there has to be some delta greater than 0, such that for all x in S, where this inequality is true, we have that all the function values at the x values that satisfy this inequality for the delta that we found, we have that f of x minus the limit is less than epsilon. So think of it as we're given some box that we need to constrain the distance from this limit value. There has to be something that's placing you in this box. What's placing you in the box in this case is the function, but where we are in the box depends on the function value. So we have this delta that constrains the function values from this accumulation point. And as long as it stays less than this delta, then we know that the distance of these function values at these input values is, in the limit, the distance between them, is less than epsilon. So hopefully that made sense, and that's the general idea behind the definition.